Have you ever stopped to think that a single accidental cut, just one copper cable, could actually plunge an entire country into like a 5-hour digital blackout?
It sounds dramatic, but it's true.
Right. Or that a big cloud service outage, something going down for just a few hours, could cost major businesses, Quora, Business Insider, millions.
Yeah, these aren't hypotheticals, they're real events.
They really show how incredibly delicate yet powerful this whole digital world we rely on is.
Absolutely.
From the cloud right down to your smart coffee maker, everything seems to be connected now.
And it all comes back to data communications. That's the foundation.
Exactly. So as we unpack all these vital topics today, make sure you hit that like button, subscribe to the deep dive if you haven't already.
Yeah, and share this deep dive with anyone you think might be looking to boost their career in this digital world.
Definitely. You won't want to miss some of the insider tips we'll be sharing, things that could really help position you for a bright future.
And remember, check the description below. We've put together some additional resources there that we think you'll find really valuable.
Okay, welcome everyone to the deep dive. Today we are embarking on a pretty crucial journey into the world of data communications.
Yep.
Now, this deep dive is specifically tailored, we think, for students of BCIS 1347 at Tarleton State University's Dr. Sam Peck College of Business.
Right, but honestly, it's for anyone who's keenly interested in information systems, computer networking, cybersecurity.
The whole field, really. Our mission today is to, well, extract the most important nuggets of knowledge. We're drawing heavily from the CompTIA network plus Guide to Networks Chapter 1 and some other key sources, too.
We want to explore those foundational concepts, the technologies, and crucially, the managerial insight.
Because it's not just academic theory, is it? It's got to be profoundly practical for your future careers.
That's the goal. We're blending that academic rigor you get in class with real-world tech applications. How does this stuff actually work out there?
And what's truly foundational here, I think, is how these connections, which seem almost invisible sometimes, they really form the strategic backbone of every modern business.
Exactly. Understanding data communications isn't just about memorizing technical terms, though that's part of it.
Sure.
It's really about grasping the essence of how information flows.
Mm-hmm.
That flow enables everything from global e-commerce right down to your daily video calls.
So we're going to connect the dots, right? Between the theory, the book knowledge, and the so what for your professional growth.
Yeah, helping you get ready for those industry standard challenges, maybe even certifications like the CompTIA network plus lineages. We'll cover the basics of how data travels, the hardware, the software.
And then dive into the really critical managerial side, the troubleshooting skills you need to keep these systems resilient and secure.
The big picture view.
Okay, let's unpack this then. We use terms like data communications all the time, but for someone maybe just starting out in networking, what is actually happening? What's the fundamental activity when we communicate digitally? How does it all kick off?
Right. Well, at its absolute core, data communication is simply the process of exchanging data, digital or sometimes analog, between two or more devices.
Okay.
Think of it like any conversation, really. But instead of voices traveling through air, it's information moving through some kind of medium.
Gotcha.
And for this to happen reliably, you need 5 essential components. Think of these as the basic building blocks for any digital interaction.
Okay, what are they?
First, you need a sender. That's the device initiating the data. It could be your computer, your phone, a server somewhere.
The starting point.
Exactly. Second, the receiver. That's the device destined to get the data, the endpoint.
Makes sense.
Third is the message or data itself, the actual information being sent, text, images, audio, video, whatever it is.
The content.
Fourth, the medium. This is the physical pathway the data travels along. It could be a copper wire, a fiber optic cable, or even, wireless signals going through the air.
The road it travels on.
Yep. And finally, maybe the most crucial piece is the protocol.
Ah, the protocol. That's like the language of the network, right? The rules of the road.
Exactly. The protocol is the set of rules, the formats, the whole sequence of operations that governs how the sender and receiver communicate.
Okay.
Without an agreed-upon protocol, the devices would just be, shouting digital noise at each other. Nothing would get through reliably.
Like trying to have a conversation where one person speaks only French and the other only Japanese with no translator.
Precisely. Let's use that conversation analogy again. You, the sender, have something to say, the message.
Right.
To me, the receiver. Through the air, that's our medium. But critically, we're following the rules of English, the grammar, the etiquette, That's the protocol.
That shared understanding makes it work.
Exactly. That shared understanding makes communication possible.
That language of networks idea really helps clarify it. So if TCP/IP is the big one, the sort of universal translator, the most common protocol suite that nearly all network devices understand.
Yeah.
What was it like before TCP/IP? And what core problem did its connection-oriented, reliable nature actually solve that let the internet boom like it did?
Oh, that's a fantastic question because it really gets to the strategic brilliance behind TCP/IP's design.
Yeah.
Before TCP/IP really took hold, you had this messy situation, a patchwork of different networks, often using proprietary protocols that just couldn't talk to each other easily.
Like isolated islands?
Exactly. Getting them to communicate was incredibly difficult, sometimes impossible. TCP/IP came along to solve this by offering a standardized open language that any network could adopt.
Open being the key word there.
Absolutely. But its most significant contribution, especially from the TCP part, is reliability.
How so?
TCP ensures that data packets, these little chunks of data, arrive in the correct order, without errors, and crucially, that any packets that get lost along the way are retransmitted.
Ah, so it checks and double checks.
Precisely. This connection-oriented, reliable nature was a total game changer. It's what paved the way for robust applications like e-commerce, secure online banking, reliable file transfers, things where you absolutely need every single piece of data to arrive intact and in the right sequence.
Right, you can't have your bank balance missing a few zeros because a packet got lost.
Exactly. Without that fundamental reliability, the internet would likely have stayed a much more limited, fragmented tool, maybe just for academics or researchers.
That makes perfect sense. A huge strategic advantage, connecting all those different systems reliably. And it's not just sending one massive block of data all at once, is it? It's broken down.
Precisely. And how that data actually travels using these protocols is fascinating in itself. Instead of trying to send one huge file in one go, computers break the data down into these small chunks, typically around 1,500 bytes each.
Why so small?
It's not arbitrary. It's a very strategic engineering decision. First, it allows other computers on the network a chance to transmit their own data during the pauses. It keeps things fair.
Ah, polite network sharing.
Kind of. It also gives the receiving computer time to process the incoming data, maybe write it to a hard drive, without getting overwhelmed.
Okay.
Plus, it lets a device receive data from multiple sources simultaneously. Think about loading a web page with images from different servers.
Right, it all comes together.
And it lets the sending computer do other things while transmitting. But maybe most importantly, if an error happens and a chunk gets corrupted or lost.
You only have to resend that small chunk.
Exactly. Not the entire massive file. That efficiency and resilience are absolutely key to keeping networks flowing smoothly, especially when things get busy.
Okay, so data travels in these small chunks. We often hear the terms packets and frames thrown around. Can you break down the difference quickly, maybe using that mail analogy?
Absolutely. Think of a packet like your letter. It has the basic address information, specifically the IP address, which is like the zip code. It tells the network the general area or network the data needs to reach.
Got it. Zip code for the network.
Now, a frame. Think of that as the packet inside a specific mail carrier's delivery truck. The frame adds more specific addressing the MIC address.
The MIC address.
Yeah, the media access control address. It's like the unique street address for a specific device on the local network segment. The frame also includes error checking information, like making sure the delivery truck arrived without losing anything crucial along that specific leg of the journey.
Ah, okay. So the frame is the packet plus that local delivery info and the error check, and make sure it gets to the right doorstep on that street.
You nailed it.
And that whole process of adding those addresses, the IP address for the packet, the MIC address for the frame, and adding other control information, often in headers at the front and trailers at the end, and that's called encapsulation, right?
Perfect. Encapsulation. It's like putting the letter data into an envelope packet and then giving that envelope to the specific mail carrier frame with detailed instructions for each step of the delivery. It's fundamental to how data moves through the different layers of a network, which we'll get into later.
Okay, cool. So beyond just sending and receiving, the actual transmission itself can happen in different ways depending on the direction of flow.
Exactly. We can categorize data transmission based on the direction of information flow. First, you have simplex transmission.
Simplex?
Yeah, it's strictly unidirectional, one way only. The sender sends, the receiver only receives. There's no mechanism for sending anything back, no error checking or retransmission request.
Right.
Think of traditional radio or TV broadcasts. The station sends the signal out, your radio just receives it. Or even simpler, typing on your keyboard. The keyboard sends signals to the computer, not the other way around.
Right. Okay, makes sense. What's next?
Then we move up to half duplex. This is bidirectional, meaning data can flow both ways, but only one direction at a time.
Ah, like a walkie-talkie.
Exactly like a walkie-talkie. You press the button to talk, then you release it to listen. The other person can't talk while you are. Older LAN technologies often use this method.
So it's slower than talking at the same time, but maybe more efficient use of a single channel?
Precisely. It optimizes a single communication channel, especially when you don't absolutely need simultaneous two-way comms, or maybe bandwidth is limited.
Okay. And the third type?
That brings us to full duplex. This is bidirectional and simultaneous. Both parties can send and receive data at the exact same time.
Like a regular phone call.
Perfect example. Or modern video conferencing. You can talk over each other, thankfully or not. This is the fastest mode, and it's standard in most newer LAN technologies and internet connections.
But it needs more capacity, right? Because you've got data flowing both ways at once.
Essentially, yes.
Yeah.
It effectively utilizes twice the transmission bandwidth because it's using two separate channels concurrently, one for sending and one for receiving. Got it. Simplex, half duplex, full duplex. Directions of flow. What other ways can we categorize transmission?
We can also look at the level of synchronization between the sender and receiver. Here we have synchronous transmission.
Synchronous sounds like in sync.
Exactly. Data is transmitted in a continuous, unbroken stream, and both the sender and receiver are perfectly synchronized by a shared clock signal. This keeps everything timed precisely.
Where would you use that?
It's highly efficient and common in high-speed technologies like Ethernet and fiber optics. It's ideal for transferring large amounts of data quickly for real-time applications and over long distances where that timing precision is critical.
Okay, so what's the alternative?
The alternative is asynchronous transmission. Here, data is sent at irregular intervals, not in a continuous stream.
How does the receiver know when data starts and stops then?
Good question. Each character or small block of data is framed with special start and stop bits. These bits tell the receiver exactly when a unit of data begins and ends, eliminating the need for that constant shared clock signal. Ah, so it's less about perfect timing and more about clear signals for each piece.
Right. This makes it very reliable, especially at slower speeds, and often more cost-effective for simpler devices. The classic example is your computer keyboard input again. Each time you press a key, that character is sent asynchronously with its own start and stop bits.
That makes sense. And there's one more category.
Yes, the number of bits sent concurrently. You have serial transmission, where bits are sent one at a time, sequentially, down a single wire or channel.
Like a single file line.
Exactly. It's generally better for data integrity over long distances because there's less chance of interference between bits, and it requires fewer physical wires, which is good for cost and simplicity, especially when sending smaller amounts of data.
And the opposite.
The opposite is parallel transmission. Here, multiple bits are sent simultaneously over multiple parallel channels or wires.
Like a multi-lane highway.
Perfect analogy. This is obviously much faster for transferring large amounts of data quickly, but usually only works well over shorter distances.
Why short distances?
Because having multiple wires running close together increases the risk of interference between them, a phenomenon called crosstalk. Also, it's generally more costly due to the extra wiring. Think about the connection between your old computer and its printer that often used a parallel cable for speed over short distance.
Okay, so serial for distance and simplicity, parallel for speed over short distances. Understanding all these modes, simplex, half-full duplex, synchronous, asynchronous, serial, parallel, seems really fundamental for grasping how different network technologies actually work.
It absolutely is. It directly relates to those course outcomes about identifying telecommunications and data communications fundamentals and explaining the characteristics of different transmission media.
Yeah.
You need this base to make informed choices later.
Right. Now let's shift gears slightly and talk about something everyone cares about. Speed. The data transfer rate, or DTR.
Ah, yes, the need for speed.
So DTR is basically how fast data moves from point A to point B, right? Whether that's across a network or just copying files to a USB drive.
Exactly. It's the measure of data movement speed. We calculate it pretty simply. Take the total amount of data transmitted, usually in bits, and divide it by the time it took in seconds.
And the units we hear are things like BPs, KBPs, MBPs, GBPs.
Right. Bits per second, kilobits per second, thousands, megabits per second, millions, and gigabits per second, billions. So if you transfer, say, an 80 megabit file and it takes 20 seconds.
80 divided by 20. That's 4 megabits per second. 4 megabits, precisely.
That's your DTR for that transfer.
But it's not always that simple, is it? Lots of things can affect that speed.
Oh, absolutely. Several factors significantly impact the actual DTR you experience, and understanding these is key for anyone managing or troubleshooting a network. First up, network congestion.
Rush hour on the data highway again?
Exactly. When the network resources, the bandwidth, the routers, the switches are all being used near their maximum capacity, things slow down. Packets get delayed, maybe even dropped. This directly impacts productivity.
Okay, congestion. What else?
Then there's network latency. Latency is the time delay it takes for a single bit of data to travel from the sender to the receiver. Think of it as the travel time.
So high latency means slower speeds.
Generally, yes, especially for interactive applications. If data has to travel a very long physical distance, like bouncing off a satellite, the latency will be high, and that delay slows down the overall back-and-forth communication needed for a fast transfer rate. It's like that noticeable delay on an international phone call sometimes.
Gotcha. Latency is delay. What about bandwidth?
Bandwidth is the capacity of the connection per second. Sticking with the highway analogy, bandwidth is the number of lanes on the highway. More lanes mean more cars. Data can travel simultaneously, allowing for a potentially higher DTR.
So bandwidth is the potential, DTR is the actual speed achieved.
That's a great way to put it. Bandwidth is the theoretical maximum, while DTR is the actual throughput you get, which is affected by latency, congestion, and other factors.
Like the type of connection.
Definitely. The type of connection matters hugely. Wired connections like Ethernet are generally faster and more reliable than wireless Wi-Fi. And within wired, fiber optic cables using light pulses are significantly faster than traditional copper cables using electrical signals. Okay. And hardware. Can my own computer slow things down? Absolutely. Limited hardware and software resources on either the sending client or receiving server end can create bottlenecks. If your computer doesn't have enough processing power, CPU, memory, RAM, or fast enough storage, like an old hard drive versus an SSD, to handle the data flow, it doesn't matter how fast the network connection is.
The whole chain is only as strong as its weakest link.
Exactly. And poorly optimized software can also hog resources and slow things down. Even things like load balancing, which is supposed to help distribute traffic, can sometimes cause issues like overloads or packet loss if it's not configured properly for high volumes.
Wow, lots of potential choke points. So how do big global services try to overcome some of these issues, especially latency for users far away?
That's where content delivery networks, or CDNs, come into play. They are absolutely crucial for the modern internet experience.
What exactly is a CDN?
A CDN is basically a large, geographically distributed network of proxy servers. These servers store copies, or caches, of website content like images, videos, and scripts.
So they spread the content out.
Precisely. The goal is to improve speed and reliability by minimizing latency. When you request content from a website that uses a CDN, the CDN automatically figures out which of its servers is geographically closest to you.
Ah, so instead of fetching data from a server maybe across the ocean?
It delivers the content from a server maybe just a city or state away. This dramatically reduces the physical distance the data has to travel, cutting down latency and making websites load much faster for users everywhere.
Clever. So it helps with speed and reliability?
Yes, and more. CDNs are great at optimizing how dynamic content is cached, managing large traffic spikes, like during a big sale or news event, and they also play a significant role in mitigating distributed denial of service, or DDoS, attacks by absorbing and filtering malicious traffic.
So understanding DTR, bandwidth, latency, congestion, and tools like CDNs is really fundamental for anyone involved in networks. It ties back to identifying those technology fundamentals and understanding media characteristics.
Absolutely. You need to grasp these concepts to select the right technologies, troubleshoot performance issues, and design efficient networks.
Okay, this raises a really important question then. If data flows in all these different ways and speed is affected by so many things, what are the actual physical and logical components that make up these networks? How are they actually built and organized?
Right. Let's get down to the building blocks. At its most basic level, remember, a computer network is just two or more computers connected by some kind of transmission medium, allowing them to share resources or communicate.
And computers here doesn't just mean desktops or laptops, right?
Not at all. Many specialized network devices, we're talking workstations, servers, routers, switches, even firewalls, are essentially specialized computers at their core, optimized for specific networking tasks.
Okay, so let's talk about the tangible stuff first. The hardware components that form the physical infrastructure. Where do we start?
Let's start with the Network Interface Card, or NIC. You'll find one in almost every network-connected device. It's the hardware module, sometimes built right onto the motherboard, sometimes an add-in card, that provides the physical connection point to the network medium.
Like the Ethernet port on your laptop?
Exactly. Or the Wi-Fi adapter. Its job is crucial. It converts the digital bits from your computer into electrical signals for copper, light pulses for fiber, or radio waves for wireless that can actually be sent across the network medium, and vice versa for receiving data.
And you mentioned a troubleshooting tip for NICs earlier.
Yes. Always check the little LED lights on or near the port. A solid green or amber light usually means you have a good physical connection. Layer 1 is okay. Blinking typically indicates network activity, data flowing. If those lights are off, you likely have a physical connection problem. Maybe the cable is unplugged or damaged, or the NIC itself has failed. A failing NIC can cause really frustrating intermittent errors that make you chase ghosts elsewhere in the network.
Good tip. Check the lights first.
Mm.
Okay, what about devices that connect multiple computers together, like hubs?
Right, hubs. These are pretty old school now. You don't see them much in modern business networks. They're simple layer 1 devices. Think of them as basic signal repeaters. Any data that comes into one port on a hub gets blindly repeated and sent out to all other connected ports.
So not very efficient. Everyone hears everyone else's conversation.
Exactly. It creates unnecessary traffic called collisions if two devices try to talk at once. And because it's a single point of failure, if the hub dies, all devices connected to it lose network connectivity. They increase network traffic dramatically because of all the broadcasting.
So what replaced hubs for better efficiency?
Switches. Switches are much smarter. They operate primarily at layer 2, the data link layer.
Layer 2. That means they understand AMC addresses, right? The street addresses.
Precisely. When a switch first starts up, it listens to the traffic and builds a table called a AMA address table or CAM table that maps the unique AMA address of each connected device to the specific physical port it's plugged into.
So it learns who lives where on its network segment?
Exactly.
Yeah.
Then, when data arrives destined for a specific MAC address, the switch looks up that address in its table and forwards the data only out the corresponding port. It doesn't just blast it everywhere like a hub.
Much more efficient. Reduces traffic, prevents collisions.
Vastly more efficient. Switches are the foundation of most modern LANs. They can also segment networks logically using virtual LANs or VLANs, which lets you group devices together regardless of their physical location, improving security and organization.
And if a switch fails?
The switch failure can still affect multiple devices, potentially an entire department depending on how the network is structured. Looking at the switch's MC address table is a key troubleshooting step if specific devices can't communicate.
Okay. Hubs repeat blindly, switches forward intelligently within a local network. What about connecting different networks together, like connecting my office LAN to the internet?
That's the job of the router. Routers are layer 3 devices. They understand logical IP addresses, not just physical MC addresses.
Layer 3, the network layer. They handle the zip codes.
Right. Their main job is to manage traffic between different networks. They look at the destination IP address in a packet and consult their routing table, a map of known networks, to determine the best path to forward that packet towards its final destination. They act as the gateways between networks.
So they make the decisions about where data should go next on its journey across the internet or between different company sites.
Exactly. They find the best path. If a router fails, devices on its local network typically lose access to remote networks, including the internet. That's why testing connectivity to and through routers using tools like Ping and Tracert is fundamental network troubleshooting.
Makes sense. Now, none of this works without the physical connections, the cabling.
The lifelines. You've got several main types. Fiber optic cables use pulses of light traveling through thin strands of glass or plastic.
Super fast, right? And long distances.
Incredibly fast, capable of very high bandwidth, and can transmit signals over much longer distances than copper without significant signal loss. But they are more expensive and delicate. They can be damaged by rough handling, tight bends, micro bends, and even environmental factors like heat or moisture over time.
Okay, fiber for speed and distance, but handle with care. What about the more common stuff?
That would be UTP-STP copper cabling. UTP is unshielded twisted pair. STP is shielded twisted pair. These are the familiar Ethernet cables categorized by performance standards like KD5E, CT6, ET6A, etc.
Twisted pair. Why are the wires twisted?
The twisting helps cancel out electromagnetic interference, or EMI, from external sources and also reduces crosstalk, which is interference between adjacent wire pairs within the same cable. SDP adds an extra layer of metallic shielding for even better protection in electrically noisy environments.
And their weaknesses.
Copper cables are susceptible to physical damage breaks in the wire, faulty connectors, those little RJ45 plugs. They have distance limitations, usually around 100 meters for Ethernet, and they are much more vulnerable to EMI and crosstalk than fiber, especially UTP.
And the last type.
Coaxial cable, like the kind used for cable TV. It has a central copper conductor, insulation, a braided metal shield, and an outer jacket. It's less common in modern lands, but still used for broadband internet access from cable providers and some other specific applications.
So choosing the right cable type, fiber, copper, UTP, STP, coax, depends entirely on the requirements for speed, distance, budget, and the environment.
Exactly. Identifying these components, their functions, and common failure modes is crucial for meeting those learning outcomes about network infrastructure, selecting appropriate cables and connectors, and designing a network that meets specific requirements.
Okay, one more hardware piece before we move to software. Wireless access points, or WPs.
Right. WPs act as a bridge between a wired network and wireless devices. Your laptop, phone, tablet connect to the WA using Wi-Fi signals, and the WILV typically connects back to the main network, usually a switch via a standard copper Ethernet cable.
So they translate between the wired and wireless worlds?
Precisely. If your wireless client suddenly can't access resources on the wired network or the internet, the WAP itself is a prime suspect, after you've ruled out configuration issues like incorrect passwords or network settings on the client devices.
Got it. Okay, that covers the main hardware. What about the software components?
Networks rely just as much on software. You have network clients and servers. Client software is what requests resources or services. Think of your web browser asking for a web page, or your email client fetching new messages.
And the server software?
Server software provides those resources or services. It runs on server machines, listens for incoming requests from clients, and then fulfills them. Examples include web server software like Apache or I, email server software like Microsoft Exchange, or file server software.
So it's a request-response relationship managed by software.
Exactly. And bridging the gap between the application software and the physical hardware, like the NIC, is the network interface software component, often part of the operating system's networking stack. It handles the low-level details of actually formatting the data, interacting with the NIC driver, and receiving it across the medium according to the chosen protocols.
Okay. Hardware provides the physical path, software manages the communication flow. Now, how are these networks typically organized? You mentioned different models earlier.
Right. The network models describe the overall architecture and how resources are managed. The simplest is the peer-to-peer, P2P model.
Peer-to-peer, like computers talking directly to each other.
Essentially, yes. In a P2P network, each computer runs its own operating system, like Windows or Mac OS, and is responsible for controlling access to its own resources, files, printers, etc. There's no central server managing things.
What are the pros and cons?
The advantage is simplicity and low cost. It's easy to set up for a very small number of computers, say less than 10, maybe in a home office. People can just share files directly.
And the downsides?
The main disadvantages are that it's decentralized, meaning managing users and security is a hassle because you have to do it on each machine individually. Doesn't scale well. Imagine managing 50 computers this way. Security is generally weaker, and it just becomes impractical for anything beyond a very small group.
So what's the alternative for businesses or larger organizations?
That would be the client-server model. This is the dominant model in business environments.
How does that work?
In this model, you have dedicated servers that provide centralized services and resources, and clients, workstations, laptops, that access those resources. Everything is managed by a specialized network operating system, NOS, running on the servers.
Like Windows Server.
Exactly.
Yeah.
A key component is often a centralized directory database, like Microsoft's Active Directory. This database stores user accounts, security permissions, information about network resources, all in one place.
So much easier to manage.
Absolutely. The advantages are centralized administration, manage users, security, backups from one place, scalability, easier to add more users and resources, and generally much stronger security.
Any downsides?
The main drawbacks are the increased cost and complexity. You need dedicated server hardware, the NOS software licenses, and someone with the expertise to configure and manage it all. But for any organization of significant size, the benefits of control, security, and scalability far outweigh these costs. It's the strategic choice for business.
Okay, P2P for small simple. Client server for most business needs. Now, what about the physical or geographical size of the network? the scope.
Right, network scope is important. The smallest is usually a local area network, LAN. This is typically confined to a small geographical area, like a single office floor, an entire building, or maybe a group of buildings close together like on a small campus. The devices are usually connected by switches.
My home Wi-Fi network is a LAN, basically.
Yep, a small home LAN. Then when you start connecting multiple LANs together, often using routers, you create an internetwork.
Why connect LANs? Why not just have one giant LAN?
Several reasons. You might need to logically separate different user groups, like accounting versus engineering, for security or organizational purposes. A single LAN might just become too large and inefficient with too much broadcast traffic. Or the physical distances between groups might exceed the limitations of standard LAN cabling and devices, requiring routers to bridge the gap.
Okay, so internetworks are collections of LANs. What's bigger?
You might have a metropolitan area network, MANN, or campus area network, CAN. These terms are sometimes used interchangeably. They describe a network that connects multiple LANs within the same larger geographical area, like a city or a large university campus.
Yeah.
Think of Tarleton State's network connecting all its buildings. That's a CAN.
Got it. And the biggest scale?
That's the wide area network, WAN. A WAN spans a broad geographical area, connecting LANs that could be in different cities, states, or even countries. Companies use WANs to connect their various branch offices back to headquarters. And of course, the ultimate WAN.
The internet.
The internet. It's the largest, most complex, and most varied WAN in existence, connecting millions of smaller networks all over the globe.
So understanding these scopes, LAN, internetwork, MAN, CAN, WAN, really helps visualize how networks are structured, from your desk all the way out to global connectivity.
Exactly. It helps you understand why accessing a server across the country requires different technologies, like routers and WAN links, than just printing to the printer down the hall, a simple LAN connection. It relates back to identifying network infrastructure and selecting the right components for the specific requirements of scale and distance.
Okay. Now, within these networks, what are the essential key network services that actually make them useful, the things we interact with?
Right, the services are the engines driving the digital world. A huge one is web services. This is what lets you browse websites. It relies on protocols like HTTP, Hypertext Transfer Protocol, and for secure connections, HTTPS, HTTP Secure, which layers HTTP over encryption protocols like SSL/TLS.
And the software running these.
Popular web server software includes Apache, very common open source, Nginx, also popular, known for performance, and Microsoft Internet Information Services, ICALS. One of these is likely powering almost every website you visit.
Okay. Web services. What else is critical?
Email services, still a cornerstone of business communication. For sending email, the standard protocol is SMTP, Simple Mail Transfer Protocol. For receiving email, you typically use either POP3, Post Office Protocol 3, or IMA4, Internet Message Access Protocol 4.
What's the difference between POP3 and IMA4?
Basically, POP3 usually downloads emails to your local device and removes them from the server, while IMA4 synchronizes your emails across multiple devices, leaving them on the server. IMA is generally preferred now for multi-device access.
And the software.
On the server side, Microsoft Exchange Server is very common in businesses. On the client side, you have applications like Microsoft Outlook, Apple Mail, or web-based clients like Gmail or Outlook on the web.
Got it. Web email. What's that critical invisible service you mentioned?
Ah, yes. DNS, the domain name system. DNS is absolutely fundamental to navigating the internet. Its job is to translate the human-readable domain names we type into browsers, like www.tarleton.edu, into the numerical IP addresses, like 192.168.1.1, though that's a private one, that computers actually use to locate each other.
So it's like the phone book of the internet.
Perfect analogy.
Yeah.
It's the first thing that happens behind the scenes whenever you navigate to almost any website. Without DNS, you'd have to memorize long strings of numbers for every site you want to visit. It's a basic necessity for accessibility.
Okay, DNS is crucial. What other services are key in business?
Database services. Businesses run on data. These services use database management systems, DBMS, the Microsoft SQL Server, Oracle Database, MySQL, PostgreSQL to store, manage, and retrieve vast amounts of structured data, usually in tables. The standard language for interacting with these databases is SQL, Structured Query Language.
And transferring files.
That's FTP, File Transfer Protocol Service. It's specifically designed for transferring files between computers. For secure transfers, you'd use FTPS, FTP Secure, using SSL/TLS, or SFTP, SSH File Transfer Protocol. Common client applications include FileZilla or CyberDuck.
Okay. And managing computers from afar.
That falls under Remote Access Service. This allows users or administrators to connect to and control a computer located elsewhere. Older, insecure protocols like Telnet should generally be avoided because they transmit data, including passwords, in plain text.
So what are the secure options?
The standard secure options are SSH, Secure Shell, which provides an encrypted command line interface, and RDP, Remote Desktop Protocol, commonly used for accessing graphical desktops on Windows machines securely.
Wow. So configuring all these different services, web, email, DNS, databases, FTP, remote access, making sure they work correctly and securely based on specific business requirements, that's a huge part of network administration.
It absolutely is. It directly maps to that learning outcome about configuring network connections and services for a given set of requirements. It's where the theory meets practical application daily.
Okay, this is fascinating. We've got the components, the models, the scope, the services, but here's where it gets really interesting for me. With all these different pieces, how do they actually coordinate? How do they all talk to each other in a standardized way? You mentioned protocols, but is there a bigger picture?
There is, and you hinted at it earlier. The answer lies in a fundamental conceptual framework that's often called the Rosetta Stone of networking, the OSI model.
OSI, Open Systems Interconnection.
That's the one. The OSI model isn't a physical thing or a specific protocol itself. It's a conceptual framework. It breaks down the incredibly complex process of network communication into 7 distinct manageable layers.
7 layers. Why so many?
The beauty of it is modularity. Each layer is designed to handle a specific set of tasks related to communication, and critically, each layer is theoretically independent. It only needs to know how to interface with the layer directly above it and the layer directly below it.
So changes in one layer shouldn't break the others?
Exactly. This modularity is incredibly vital. It allows different vendors to develop hardware and software for specific layers, like NICs for layer 12 or routing software for layer 3, knowing that if they follow the standards, their products should interoperate with products from other vendors handling different layers. It's also invaluable for troubleshooting.
How does it help troubleshooting?
The OSI model provides a common language and a systematic approach. When something goes wrong, say, you can't access a website, network engineers and technicians can use the model to pinpoint which layer the problem likely resides in. Is it a physical connection issue, layer 1, a local addressing problem, layer 2, a routing issue, layer 3, a web protocol issue, layer 7.
So it drastically narrows down the search.
Tremendously. Instead of randomly checking everything, you can systematically test layer by layer. It's truly the blueprint for understanding network architecture and a cornerstone for facilitating troubleshooting techniques, a key outcome for students.
And you mentioned something called a PDU.
Right. As data moves down through the layers on the sending computer, getting encapsulated, or up through the layers on the receiving computer, getting de-encapsulated, the chunk of data at each layer is technically referred to as a protocol data unit, or PDU. The specific name changes at different layers. It might be called a segment, packet, or frame. But PDU is the generic term for that unit of information as it passes between layers.
Okay, 7 layers. Let's start at the bottom. Layer 1, the physical layer.
Layer 1 is all about the physical transmission of raw bits across the network medium. It deals with the tangible stuff, the voltages on a copper wire, the frequencies of radio waves for Wi-Fi, the pulses of light in a fiber optic cable. It defines the electrical, mechanical, and procedural specifications for the physical link.
So cables, connectors, NICs are involved here.
Cables and connectors, definitely. Devices that operate purely or primarily at layer 1 include repeaters, which just regenerate and amplify a signal to extend its range, and hubs, which, as we said, repeat signals to all ports. NICs actually bridge layer 1 and layer 2. They handle the physical signaling, layer 1, but also deal with MAC addressing, layer 2.
And troubleshooting layer 1.
It's purely physical or electrical. Remember the Georgian woman cutting the cable, classic layer 1 failure? Is the cable plugged in securely? Are the link lights on the NIC and the switch port lit up? Is the cable damaged? Is there interference? If the physical link isn't established, nothing else up the stack can work. It directly relates to identifying those infrastructure components and applying basic troubleshooting.
Okay, physical bits on the wire. What's next? Layer 2, the data link layer.
Layer 2 takes the raw bits from layer 1 and organizes them into frames. Remember our mail analogy? Layer 2 adds the physical source and destination as IGS addresses the street addresses for the local network segment. Crucially, it also adds error detection information, usually a frame check sequence, FCS, to ensure the frame wasn't corrupted during its trip across that specific link.
So its job is reliable delivery between adjacent nodes on the same network.
Exactly. error-free transfer of data frames between nodes on the same physical network segment. The key devices operating here are switches, which use those MEA addresses learned in their tables to make intelligent forwarding decisions, sending frames only where they need to go on the local network. NICs, as mentioned, also operate significantly at Layer 2.
And troubleshooting at Layer 2.
Common tasks include checking the switch's MAC address table. If a device isn't communicating, is its MAC address even showing up in the table? Is it associated with the correct port? Another major issue specific to Layer 2, especially in networks with redundant switch connections designed for resilience, is the potential for switching or bridging loops.
Loops. That sounds bad.
Very bad. If you have multiple paths between switches and don't have a mechanism to manage them, frames can enter an endless loop, bouncing back and forth forever. Because Layer 2 frames don't have a time-to-live counter like Layer 3 packets do, they never expire.
What happens then?
This quickly leads to a broadcast storm, where the looping frames, often broadcast initially, multiply and consume all available bandwidth, grinding the entire network segment to a halt. It's catastrophic.
How do you prevent that?
The standard solution is the Spanning Tree Protocol, STP, or its faster variants like RSTP. STP runs on switches and intelligently detects redundant paths, then logically blocks traffic on some of those paths to ensure there's only one active route between any 2 points at any given time, preventing loops while still allowing for failover if the primary path goes down. Understanding Layer 2 architecture and potential issues like loops is vital for troubleshooting switched networks.
Wow, STP sounds critical. Okay, Layer 2 handles local delivery using MSC addresses. What about getting data between different networks?
That brings us to Layer 3. The network layer. This is where the magic of internet working happens. Layer 3 is responsible for logical addressing, routing, and forwarding of data packets across different networks.
Yeah.
Its job is to find the best path to get data from its source network all the way to its destination network, potentially traversing many intermediate networks like the internet.
And this is where IP addresses live.
Exactly. The primary protocol here is the Internet Protocol. IP. We have the older but still widely used IPv4 with its 32-bit addresses like 198.51.100.1, which has largely run out of unique public addresses.
In the future.
The future, and increasingly the present, is IPv6, which uses much longer 128-bit addresses, looking something like 2001.0db8.85A3.000.83e.8370.7334. IPv6 provides a virtually inexhaustible supply of addresses and has other improvements, but adoption is still ongoing.
So Layer 3 assigns these logical IP addresses.
Yes, and manages them. Key services operating at Layer 3 include IP addressing itself. This can be done manually, statically assigning an IP,
Right.
or much more commonly, automatically using protocols like DHCP, Dynamic Host Control Protocol, for IPv4. DHCP servers automatically assign clients an IP address, subnet mask, default gateway router address, and DNS server addresses.
Makes it up much easier.
Definitely. For IPv6, there's DHCPv6, but also SLAAC, Stateless Automated Address Configuration, which allows devices to configure their own addresses based on network information advertised by routers.
What else happens at Layer 3?
Another absolutely crucial protocol is ARP, Address Resolution Protocol for IPv4, or Neighbor Discovery Protocol for IPv6. Remember how Layer 2 needs MMAN addresses for local delivery, but Layer 3 works with IP addresses for end-to-end routing?
Right. How do they connect?
ARP is the translator. When a device needs to send a packet to another device on the same local network, it knows the destination IP address, but needs the corresponding MSC address to create the Layer 2 frame. It sends out an ARP broadcast asking, essentially, who has this IP address? Tell me your MAC address. The target device replies, and the sender caches this IP to mapping for future use.
So ARP links the logical IP world to the physical MX world on the local segment.
Perfectly put.
Yeah.
We also have DNS, Domain Name System, operating here conceptually, translating names to IPs, and the core function, routing. Routers use routing protocols to learn about remote networks and build their routing tables, which tell them the best path to forward packets.
Different types of routing protocol.
Yes. Interior gateway protocols, IGP, are used within a single organization's network, an autonomous system. Examples include OSPF, EIGRP, and the older RIP. Exterior gateway protocols, EGP, are used to exchange routing information between different autonomous systems across the public internet. The main EGP used today is BGP, Border Gateway Protocol. It's essentially the routing protocol that holds the entire internet together.
Wow. And hardware at Layer 3?
Primarily routers, as we discussed, specialized hardware optimized for making complex routing decisions quickly. Also, critically, firewalls. Firewalls act as security guards between networks, inspecting traffic and blocking or allowing it based on predefined security rules, like blocking traffic on certain ports or from certain IP addresses. Next-generation firewalls, NGFWs, go even further, inspecting the actual content of packets to identify specific applications or potential threats, providing much deeper security.
And troubleshooting layer 3.
Common issues include incorrect IP address or subnet mask configurations, problems with the default gateway setting, DNS resolution failures, misconfigured routers, routing loops where packets bounce endlessly between routers due to bad routing information, or firewall rules accidentally blocking legitimate traffic. Understanding this layer is vital for configuring network connections, services, and especially security.
Okay, deep breath. Layer 3 gets data between networks. What happens next? Layer 4, the transport layer.
Layer 4 is all about the end-to-end connection management and reliability of the data transfer between the source application and the destination application. While Layer 3 gets packets to the right destination computer, Layer 4 ensures the data gets to the right process or application running on that computer, and it manages things like ensuring data arrives in the correct order without errors and controlling the flow of data.
How does it know which application to deliver to?
Using port numbers. Layer 4 adds source and destination port numbers to the data segments. Specific applications are associated with well-known port numbers. MHE web servers usually listen on port 80 for HTTP and 443 for HTTPS. This allows the receiving computer to direct incoming data to the correct application, like the web browser or the email client.
And this is where TCP and UDP come in.
Exactly. The two main protocols at Layer 4 are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. They offer different levels of service.
Remind me of the difference again?
TCP is connection-oriented and reliable. Before sending data, it establishes a connection, the famous three-way handshake. It then numbers the data segments, ensures they arrive in order, acknowledges received segments, and retransmits any that are lost or corrupted. It provides guaranteed order delivery.
Good for things like file transfers or web browsing where you need everything intact.
Perfect for those. UDP, on the other hand, is connectionless and unreliable, or rather, best effort. It just sends the data segments, called datagrams, without establishing a connection first, without numbering or acknowledgments, and without retransmitting lost data.
Why would you ever use that? Sounds risky.
Because it's much faster and has lower overhead. It's ideal for applications where speed is more critical than perfect reliability, and where losing a small amount of data isn't catastrophic. Think real-time applications like video streaming, online gaming, or VoIP, voice over IP. If you miss a tiny piece of video or audio, it's usually better to just keep going rather than pause everything to wait for a retransmission.
The trade-off between reliability and speed efficiency.
Precisely. Layer 4 makes that choice possible depending on the application's needs. Another common function related to Layer 4, especially in home networks, is port address translation, PAT, which is a type of network address translation.
NetPat.
That lets multiple devices on my home network share one public IP address, right? Exactly. Your router uses PDA to keep track of which internal device initiated which outgoing connection by assigning unique source port numbers. When the response comes back from the internet, the router looks at the destination port number, which matches the unique source port it assigned, and knows which internal device to forward the reply to. It's essential for conserving IPv4 addresses.
Clever. And you mentioned tuning TCP earlier. That happens at Layer 4.
Yes. Optimizing TCP throughput, especially over networks with high bandwidth but also high latency, like satellite links or some packet loss, involves tuning Layer 4 parameters. This includes adjusting the receive window, or WI size, which tells the sender how much data the receiver is prepared to buffer, and understanding the congestion window, CWIN, which is how much data the sender thinks it can send without overwhelming the network. Getting these window size correctly, along with appropriate retransmission timers, is crucial for performance. Even a tiny amount of packet loss, like 1 or 2%, can drastically reduce TCP throughput if these aren't optimized.
So managing Layer 4 is key for performance and reliability, tying into configuring network connections, services, and overall network management.
Absolutely. It's about ensuring the applications get the quality of service they need.
Okay, we've climbed almost to the top. We skipped layers 5 and 6, the session and presentation layers, which handle things like managing dialogues and data formatting encryption respectively. They are often handled within the application layer in the TCP/IP model. So let's jump to the top. Layer 7, the application layer.
Layer 7 is the layer that users and applications directly interact with. It's concerned with the specific protocols needed for particular applications to communicate effectively. It provides the interface between the application software and the network.
So the protocols we mentioned earlier, like HTTP, HTTPS for web, SMTP, POP3 IMAP for email, FTP for file transfer, DNS for name resolution, they all operate primarily at layer 7.
Yes, when you use your web browser, it's speaking HTTP or HTTPS at layer 7. Your email client speaks SMTP and POP3 IAMP at layer 7. These protocols define the specific commands and formats used by those applications to exchange information over the network, relying on the lower layers, like TCP or UDP at layer 4, IP at layer 3, etc., to actually handle the transmission.
So it's the layer that makes the network useful for specific tasks.
Precisely. It's where the user's requirements meet the network's capabilities. Though it's worth noting that not all systems or models strictly implement every single OSI layer as distinctly separate. The TCP/IP model, which is more commonly used in practice, maps slightly differently, often combining layers 5, 6, and 7 into a single application layer. But the OSI model's 7-layer structure remains incredibly valuable as a conceptual and troubleshooting tool.
Okay, that OSI model provides an amazing framework for understanding how it all fits together, layer by layer. But let's be realistic, networks aren't always perfect, are they?
Far from it. That's where the real challenge, honestly, where a lot of the career opportunity lies for networking professionals, comes in. Preventing problems in the first place, and quickly, effectively fixing them when they inevitably occur.
And the stakes are high, right? Network downtime isn't just an inconvenience.
It can be absolutely crippling for a business. We've seen some dramatic real-world examples. Remember that Amazon S3 cloud storage outage back in February 2017?
Vaguely, yeah.
It lasted about 5 hours, and it took down huge chunks of the internet because so many websites and services relied on S3. Big names like Quora, Trello, Business Insider were heavily affected. The estimated cost ran into the millions, possibly hundreds of millions, across all affected businesses. Even Amazon's own AWS status dashboard couldn't update because it relied on S3.
Wow, that's ironic.
Isn't it? Another example. A major global airline back in May 2017 had a massive IT systems failure. It wasn't even a hack, apparently a power supply issue that wasn't handled correctly during maintenance.
What was the impact?
A 3-day outage, over 700 flights canceled, tens of thousands of passengers stranded, and an estimated financial hit of around $80 million, not to mention the huge damage to their reputation.
Ouch. And that story you mentioned at the start, the Georgian woman.
Right, April 2011. Apparently scavenging for copper to sell as scrap metal, she accidentally severed a single underground fiber optic cable that carried a huge portion of Armenia's internet traffic through Georgia.
And the result?
The entire country of Armenia was essentially offline for 5 hours from one accidental cable cut.
That's insane. It really highlights the vulnerability. This isn't just a tech problem, it's a massive business risk.
Exactly. For business students, particularly those in BCIS 1347, this is a critical takeaway. Understanding network resilience, uptime, and disaster recovery isn't just an IT concern. It's fundamental to business continuity. Downtime directly hits revenue, erodes customer trust, and damages brand reputation in a way few other things can.
What's the typical cost? Is there an average?
Estimates vary, but studies often place the average hourly cost of downtime for small to medium businesses, SMBs, somewhere around $42,000 per hour. For larger enterprises, it can be much, much higher.
$42,000 an hour. That adds up incredibly fast.
It really does. And what's the single biggest culprit, the #1 statistically cited cause of network downtime?
Let me guess. Hardware failure.
Bingo. Simple hardware failure. Switches, routers, NICs, cables, power supplies. The physical components are often the first point of breakdown.
So how do organizations fight back against this? How do they manage networks strategically to prevent these kinds of disasters?
It comes down to adopting solid network management best practices. We've compiled a list of 11 key practices based on industry expertise that can save a business from many common network pitfalls.
Okay, let's hear them. Number 1.
Number 1, and absolutely crucial for security. Remove all L built-in configurations and reconfigure every single network device from scratch.
Why from scratch? Don't they come pre-configured?
They do, but often with default usernames, passwords like admin, password, and settings that are widely known by attackers. Leaving these defaults in place, even on features you think you're not using, creates massive security holes. Studies suggest something like 80% of data breaches involve weak or default credentials.
Wow, 8%.
Yeah, so best practice is to wipe the defaults and configure everything intentionally. Enforce strong, unique password policies, change credentials regularly, disable unused services, start clean.
Okay, crucial first step. What's number 2?
Choose the right parameters for monitoring. You don't need to monitor every single possible metric on every single device in your network. That just creates unnecessary load on the devices and floods your monitoring system with noise.
So prioritize.
Just exactly. Monitor based on device criticality. Your core routers, main servers, firewalls. Monitor them comprehensively: CPU, memory, interface traffic, errors, latency, everything. But a standard office printer or a test server, maybe just basic up-down status and network connectivity is enough. Also, monitor based on device type, for example. Monitoring CPU temperature might be critical for a server in a hot data closet, but irrelevant for a switch. Use shorter monitoring intervals, more frequent checks for your most critical devices.
Makes sense. Focus resources where they matter most. Number 3.
Monitor the interfaces in your network with as much importance as the devices themselves. This is often overlooked. Remember, hardware failure is #1, and interface issues, like a faulty port on a switch or router, account for a significant chunk of that. Maybe 25% of major downtime incidents originate at an interface.
So don't just check if the router is up, check if its ports are healthy.
Precisely. Use your monitoring tools. Leverage vendor-specific templates, if available, to get in-depth analysis of interface traffic, errors, discards. Pay special attention to critical interfaces like server connections, uplinks between switches, or WAN links. Set meaningful thresholds for alerts. Firstly, alert if error rate exceeds BOO1%, and remember to update your monitoring tool configuration whenever you make changes to interfaces.
Got it. Monitor interfaces diligently. Number 4.
This one requires a shift in mindset. Monitor for symptoms, not just problems.
What's the difference?
Monitoring for a problem is reactive, like setting an alert only when a server goes completely offline. By then, the damage is done. Monitoring for symptoms is proactive. You look for the precursor incidents or triggers that often happen before a full-blown outage, like maybe CPU utilization hitting 90% for 10 minutes straight, or interface errors slowly creeping up, or response time gradually increasing. These are symptoms. Set multiple levels of alerts, maybe a warning at 80% CPU, a critical alert at 95%. Analyze historical alert patterns. Maybe that server always spikes CPU before it crashes. That pattern is your symptom, allowing you to investigate before the crash happens. Find the root cause, not just the effect.
Proactive versus reactive makes sense. Number 5.
Effectively group devices and automate monitor association. As your network grows, managing devices individually becomes impossible. Grouping devices logically in your monitoring system, maybe by location, by type, all Cisco switches, by function, all web servers, by vendor, or even by bandwidth consumption, makes life much easier. It allows you to apply configuration changes or policies in bulk to entire groups. It simplifies reporting and analysis. For example, show me the overall health of the New York office network. And ideally, use features in your monitoring tools to automate how monitors are applied. Set up rules so that when a new device is discovered, the appropriate monitoring templates and thresholds are applied automatically based on its type or group.
Reduce manual work, improve consistency. Good one. Number 6.
Use syslogs and traps to your advantage. Standard network monitoring often relies on polling, where the monitoring system periodically asks devices, "How are you?"
Right, like checking every 5 minutes.
Exactly. But what if a critical failure happens between polls? You might not know for several minutes. Syslogs and SNMP traps work the other way around. They're messages generated by the device itself and sent immediately to the monitoring system when a specific event occurs, like an interface going down, a configuration change, a critical error.
So they provide real-time alerts for specific events.
Yes. Configure your devices to send these messages for important events, and configure your monitoring system to generate alerts based on specific syslog messages or trap types. This catches critical issues much faster than polling alone might.
Okay, leverage device-generated alerts. Number 7.
The devices you aren't monitoring are still important. This sounds obvious, but it's a common trap. Maybe you skip monitoring test servers or non-critical workstations to save on monitoring software license costs.
Seems reasonable.
But remember, hardware failure is the #1 cause of downtime, and you can never predict when a device might become critical. Maybe that test server suddenly gets repurposed for a vital function. Or maybe a failure on an unmonitored device starts flooding the network with bad traffic, impacting everything else.
The hidden risks.
Exactly. Keep an inventory of all network devices, even unmonitored ones. Reevaluate regularly if their function changes. If a device becomes more important, add it to monitoring, even if you only monitor basic parameters initially. The potential cost of downtime caused by an unmonitored device usually far outweighs the licensing cost.
Good point. Don't ignore the periphery. Number 8.
Plan change implementations meticulously. Network changes, software upgrades, configuration updates, hardware swaps are a major source of self-inflicted outages if not planned carefully.
Change management is key.
Absolutely. The goal is always minimal downtime and no impact on crucial business operations. Factors to consider include criticality. Is this an emergency security patch that needs to happen NOW, or a routine feature update that can wait for a maintenance window? Duration. How long will the change take? Can a short critical fix happen during production hours? Or does a long upgrade require off hours? Network size and redundancy. Can you perform the change on redundant systems without impacting users, or does the whole service need to go down? Recovery time. Always factor in time for rollback if the change goes wrong.
And approvals.
Crucial. Implement a clear approval hierarchy. At minimum, the person making the change, a relevant domain or networking expert, peer review, and potentially upper management should sign off on all significant changes, especially those impacting critical systems. Document the plan, the backout procedure, and the approval.
Formalize the change process. Number 9.
Don't ignore minor updates. There's often a tendency, maybe due to risk aversion, if it ain't broke, don't fix it, for admins to skip small vendor software patches or firmware updates, waiting only for major critical releases.
Why is that bad?
Because those small updates often contain prerequisites, bug fixes, or security tweaks that are necessary for future major updates to install correctly. Skipping them can lead to failed critical updates later, or even introduce new security vulnerabilities because dependencies aren't met.
Ah, the cumulative effect.
Right. Read the release notes for all updates. If possible, group multiple small, non-urgent updates together and install them during a regular, scheduled weekly or monthly maintenance window. Never just ignore updates indefinitely.
Stay current. Okay, number 10.
Automate tasks when your network is small. Don't wait until you have a huge, complex network before you start thinking about automation. Organizations often make this mistake, and trying to retrofit automation onto a large, complex, manually managed environment is much harder.
Start early, even if it seems overkill.
Absolutely. Leverage automation tools early on for even the minutest of tasks. Think about automating, adding newly discovered devices to monitoring, scheduling regular maintenance downtime, performing remote operations or configuration backups, automatically triggering actions based on thresholds, like restarting a service, repolling devices after an outage. Manual approaches are time-consuming and prone to human error. Build automation into your processes from the beginning.
Makes sense. Build good habits early. And the final best practice, number 11.
This might be the most critical one of all for overall success. Choose the right network management application. The software tool you use to monitor, manage, and automate your network is fundamental.
What should you look for?
Start with clear goals and requirements. What problems are you trying to solve? Then evaluate potential tools based on features. Does it meet your specific needs for monitoring, alerting, reporting, automation? Ease of setup and usage. Is it intuitive? Can your team learn it quickly? Scalability. Can it grow with your network? Device support. Does it support the specific hardware and vendors you use? Technical support and community. Is help available when you need it? Are there active online forums? Pricing. Does it fit your budget, including ongoing maintenance?
Don't just buy the first shiny object.
Definitely not. Always take advantage of free trials and demos. Test the tools in your own environment with your own devices before committing. Choosing the right tool upfront saves immense headaches down the road.
Okay, 11 best practices. These really emphasize being proactive, systematic, secure, and strategic. Following these seems crucial for anyone wanting to formulate risk assessments, develop security strategies, and efficiently manage network connections and services, hitting several key course outcomes.
Absolutely. They are designed to prevent issues.
Yeah.
But what happens when, despite your best efforts, something inevitably goes wrong? That's where systematic troubleshooting becomes your most valuable reactive skill.
Right. The network is down, users are complaining, the pressure is on. Where do you start?
You start with a proven methodology. CompTIA, for instance, outlines a very logical troubleshooting methodology that provides a great framework. It begins with step 1, identify the problem.
Seems obvious, but what does that really involve?
It's about digging deeper than just the surface symptom to find the root cause. For example, a user reports, "I can't log in." The symptom is the failed login, but the root cause might be anything from a forgotten password to a network connectivity issue, preventing them from even reaching the authentication server.
So gather information.
Exactly. Gather info from multiple sources. Check system log files, look for specific error messages, talk to the users experiencing the problem. What changed? When did it start? Can they reproduce it? Identify all the symptoms. Determine if anything changed recently in the environment, a software update, a hardware swap. Try to duplicate the problem yourself. The goal is to accurately define and narrow the scope of the actual issue. If there are multiple problems, tackle them one at a time.
Okay, define the real problem. Step 2.
Establish a theory of probable cause. Based on the information you gathered, make an educated guess. A guess backed by data about what might be causing the problem.
Where do you start with theories?
Start simple. Work toward the more complex. Question the obvious first. Is the device powered on? Is the cable plugged in? Then start researching. Check vendor documentation, your organization's own network diagrams and documentation. Search online IT forums, knowledge bases. For layered technologies like networking, it often helps to think systematically using the OSI model. Start checking at the bottom, physical layer, and work up, or start at the top, application layer, and work down. And critically, take careful notes of your theories and the evidence supporting them.
Okay, form a hypothesis based on evidence. Step 3.
Test the theory to determine the cause. This is still primarily an information gathering step. You're not making changes yet, you're performing tests to confirm or deny your current theory.
What kind of tests?
If your theory is incorrect IP configuration, you'd check the IP settings, ipconfig or ifconfig. If your theory is router failure, you'd use ping or tracert to test connectivity through the router. If your theory involves a specific service like DNS, you'd use nslookup. You might use more advanced tools like Nmap for network scanning or Wireshark, packet sniffer, to capture and analyze traffic for deeper clues.
And if the test proves your theory wrong?
Then you discard that theory, maybe go back to step 2, establish a theory with the new information you've learned, or even back to step 1, identify the problem. If the tests reveal the initial problem description was inaccurate, it's an iterative process.
Okay, test without changing anything yet. Once you're confident you've found the cause,
Then you move to step 4, establish a plan of action and implement the solution. Now you're ready to make changes, but plan it first.
what goes into the plan?
Think about potential impacts. Will this require downtime? What resources do you need? Software patches, new hardware, configuration files. Is there a specific sequence of steps? Do you need to test this in a staging environment first if it's a complex change? Do you need to back up data or configurations before you start? And crucially, get any necessary approvals based on your organization's change management policy.
And the most important part of the plan.
Having a rollback plan. Always know how you will undo the changes you're about to make if the fix doesn't work, or worse, makes things worse. How do you get back to the previous known good state quickly?
Plan the fix, plan the rollback, then implement carefully. What's next? Step 5.
Step 5. Verify full system functionality and implement preventive measures. This step is so often missed in the rush to close the ticket. Don't just assume your fix worked because the immediate symptom disappeared.
How do you verify?
Test thoroughly. If possible, have the original users who reported the problem test and confirm it's resolved for them, meeting their specific requirements. Check related systems. If the fix involved, say, updating a driver on one server, consider if that same fix needs to be applied preemptively to other similar servers to prevent the problem from happening there. Preventive measures.
Verify and prevent recurrence. Good. Step 6.
The one nobody likes but everyone needs. Step 6. Document findings, actions, outcomes, and lessons learned.
Why is documentation so vital?
It's essential for future troubleshooting by yourself or others. It prevents reinventing the wheel if the same problem occurs again. It provides a record of what changes were made, which is critical if you need to reverse them later due to unintended consequences. It helps in training new team members. As the source material bluntly puts it, zero documentation is a nightmare. It severely hinders team efficiency and knowledge sharing.
Document everything. Got it. And the final principle, step 7.
Step 7. Keep it simple. This is more of an overarching principle. When you start troubleshooting, back in step 2, always consider the simplest explanations first before diving into complex ones.
The old, is it plugged in? Is it turned on? Did you try restarting it? Checklist.
Exactly. It sounds basic, maybe even a bit facetious, but it embodies the spirit. Ruling out the simple stuff quickly. Physical connections, power status, basic configuration errors saves a huge amount of time before you start analyzing packet captures or debugging routing protocols. And in the real world, remember you're often working under time pressure, maybe defined by service level agreements, SLAs, so efficiency is key. This systematic methodology helps you be efficient and effective.
That CompTIA methodology provides a really solid, logical framework for tackling problems. Applying that consistently seems key for anyone needing to use appropriate network troubleshooting techniques.
It absolutely is. But beyond that step-by-step process, arguably the single most important troubleshooting tool you can possibly have isn't a piece of software. It's establishing a baseline for your network.
A baseline. What exactly do you mean by that?
A baseline isn't just running a report one time. It's an ongoing process of regularly studying, monitoring, and documenting your network's normal behavior. The goal is to define what normal actually looks like: normal traffic levels, normal error rates, normal response times, normal resource utilization under specific conditions, like peak business hours versus overnight.
Why is knowing normal so important?
Because when something goes wrong, how can you possibly identify what's abnormal if you don't know what normal is supposed to be?
You need a reference point for comparison.
Precisely. A good baseline allows you to immediately spot deviations from normal behavior, which is crucial for rapid troubleshooting. Is this spike in traffic unusual, or is it just the start of the workday rush? Is this level of packet errors normal for this link, or does it indicate a problem? A baseline answers those questions. It also helps you proactively identify potential problems before they cause outages and plan effectively for future network growth by understanding current usage patterns.
Okay, establishing a baseline is critical. How do you actually go about doing it? What's the procedure?
It's a multi-step process. First, step 1. Develop and maintain a site network map. This isn't just a rough sketch. It should be a detailed diagram showing the physical location of all your network devices: routers, switches, servers, WAPs, major workstations or workgroups, the network backbone cabling, data center layouts, wiring closets, and any remote site connections.
Physical layout. What else?
Crucially, your map should also include logical connections. Show how VLANs are configured, which subnets exist, how different network segments are interconnected logically. This helps immensely in quickly narrowing down the scope of a problem. Is the issue affecting just one VLAN? Only devices connected to a specific switch, the map tells you. And vitally, store it online where it can be easily accessed and updated, but always keep an up-to-date paper copy somewhere safe. If the network is down, you might not be able to access the online version.
Good point. Online and paper map. Step 2.
Step 2. Compile a hardware, software, and configuration inventory. Think of this as your detailed network notebook. Again, keep both online and paper copies.
What goes in the notebook?
Everything. Securely store essential information like administrative passwords, using a password manager as best practice here. Keep a detailed inventory of all network devices: make, model, serial number, IP address, physical location, connected ports, MNC addresses. For unmanaged switches, which don't provide diagnostic interfaces, you might even need to manually document which MNC address is connected to which port. Most importantly, maintain a meticulous logbook of all interactions, every configuration change, software update, troubleshooting step, observed issue with dates, times, and who did what.
That logbook sounds like the documentation from the troubleshooting methodology.
Exactly. It feeds into this baseline inventory. This detailed record is invaluable.
Okay, map and inventory. Step 3.
Step 3. Collect statistical data about your network's performance. This is where you start measuring what's actually happening. You need to capture metrics like total bandwidth utilization on your key LAN and WAN links, average and peak, inbound versus outbound traffic patterns, what protocols and ports are most commonly used, helps identify necessary versus unnecessary traffic. When are your peak utilization times? Daily, weekly, monthly, helps plan maintenance. Which network segments consistently experience the highest utilization?
How do you collect this data?
Using network monitoring software, built-in device statistics like interface counters on switches and routers, or even temporary packet capture analysis. The goal is to get a quantitative picture of your network's normal traffic flow over time.
Got the data. Step 4.
Step 4. Analyze the data and establish thresholds. Now, you take all that collected information and make sense of it to define normal and set alert thresholds. This involves several types of analysis. Physical health analysis. Compare your physical topology from the map against relevant standards, like IEC standards for cabling. Understand the documented performance limits of your hardware. Determine a normal packet error profile, for example. Some collisions might be normal on older half-duplex Ethernet, but any collisions on a modern full-duplex switched link indicate a problem, like a duplex mismatch. Broadcast analysis. Network broadcasts are normal, but too many can cause a broadcast storm. Analyze your data to determine the normal level and rate of broadcast multicast traffic on your segments, then set thresholds to alert you if it exceeds that significantly. Network capacity overload analysis. Understand your available bandwidth versus your actual utilization, average peak historical trends. Identify the saturation points. At what level of utilization do users start experiencing slowdowns or outages? This helps you plan upgrades proactively.
So use the data to define what's acceptable and what's problematic.
Precisely. You're defining the boundaries of normal operation.
And the last step, step 5.
Step 5. Fix immediate problems identified. During the process of creating your baseline, you'll almost certainly uncover existing issues, maybe misconfigured interfaces, suboptimal cabling, unexpected traffic patterns. Fix these problems as you find them. This not only optimizes performance immediately, but also ensures your baseline reflects a healthy network state, making future troubleshooting more effective.
So establishing a baseline is a major undertaking, but it pays off hugely in troubleshooting and planning.
It's fundamental. It directly supports the ability to design logical and physical networks and apply troubleshooting techniques effectively because you know what you're starting from and what you're aiming for.
Okay, baseline established. Let's dive deeper now into specific network problems and analysis. What are the common categories of issues people face?
Broadly, you can think about performance problems. Things are working, but they're slow, and connectivity problems, things aren't working at all, or only intermittently.
Let's start with performance slowdowns. What causes those?
Oh, a multitude of things. It could be poor routing decisions, sending traffic on inefficient paths, misconfigured devices, routers, switches, physically bad cabling causing excessive errors, simply overutilized capacity, congestion, malware consuming bandwidth, misconfigured WAN circuits, having too many excessive protocols running unnecessarily, overloaded servers that can't respond quickly, or even misconfigured DNS causing delays in name resolution.
You mentioned misconfigured devices. Any common configuration errors that cause slowdowns?
A really common and tricky one is duplex and speed setting mismatches. This happens when two connected devices, like a server's NIC and the switch port it's plugged into, fail to correctly negotiate or are manually set to incompatible settings.
Like one set to full duplex and the other somehow ending up at half duplex.
Exactly. Or mismatched speeds, 1 Gbps versus 100 Mbps. While basic connectivity might still work, a simple ping might even succeed, performance, especially for large file transfers, will become abysmal. You'll often see specific errors like late collisions on the half-duplex side. It's a notorious performance killer that can be hard to spot if you're not looking for it specifically in the interface statistics. Always ensure both ends are set consistently. Usually auto-negotiation works best, unless you have a specific reason to set manually.
Good one to watch out for. What else slows things down?
IP address conflicts. We touched on this. If two devices accidentally get assigned the same IP address, often happens with manual static assignments, it causes confusion. Packets might get delivered to the wrong device, leading to errors and performance issues. This is a big reason why using DHCP is strongly recommended. It prevents duplicates automatically.
And congestion.
Network congestion is a major factor. As traffic volume increases, routers and switches might start delaying packets, increasing latency, or even dropping them if their buffers overflow. This can be caused by temporary spikes, underlying issues like broadcast storms, just too many active connections for the available bandwidth, or excessive unnecessary protocols generating background noise.
Hardware failure can cause slowdowns too, not just complete outages.
Absolutely. A failing NIC might start generating excessive errors, slowing down its own communication. A faulty switch port might be dropping packets intermittently. A router with memory issues might be slow when processing routing updates. And bad cabling is a classic cause of slowdowns due to high error rates requiring constant retransmissions. Remember, hardware failure is still the #1 cause, manifesting in various ways.
We also talked about network loops causing broadcast storms. Can they cause slowdowns before total collapse?
Yes. Routing loops at layer 3 can cause packets to bounce between routers for a while before their TTL expires, consuming bandwidth and increasing latency. Switching loops at layer 2, before they escalate into a full broadcast storm, can cause intermittent connectivity and high CPU utilization on switches as they struggle with the rapidly multiplying frames. STP is designed to prevent these layer 2 loops entirely.
What about software issues?
Malware, spyware, worms, trojans is a definite performance killer. It consumes bandwidth by scanning networks, communicating with command and control servers, or spreading itself. It can also directly interfere with network configurations. And simple misconfiguration, as we keep saying, is huge. An incorrect subnet mask might allow local communication but prevent reaching certain remote networks. Wrong DNS servers mean slow or failed website lookups. The duplex mismatch we discussed. Seemingly small errors have big impacts.
Network growth itself can be a cause.
Yes, an increased number of connections just naturally puts more demand on the infrastructure. As more devices and users come online, you might simply outgrow your current bandwidth or device capacity. Solutions involve upgrading infrastructure, faster links, better switches routers, segmenting the network using VLANs to isolate traffic, or implementing traffic shaping, quality of service QoS policies to prioritize critical application traffic over less important data.
And those excessive protocols.
Right. Modern operating systems often enable many network protocols by default. If you're not using some of them, like maybe older file sharing protocols if you're using a newer method, disabling them reduces the background chatter and processing load on devices. Only run what you actually need.
Lastly, physical design.
Poor topology design, basic physical wiring issues. Are cable runs exceeding the maximum distance limits, causing signal attenuation? Is the backbone capacity sufficient for the traffic aggregating onto it? Maybe you need fiber instead of copper. Are the media connectors properly terminated and compatible? Physical layer issues often manifest as performance problems.
Okay, that's a lot of potential causes for slowdowns. What about outright connectivity problems, loss of connection, or intermittent issues?
Many of the same culprits apply. Loss of connectivity is often due to hardware failure, a dead NIC, a cut cable, a failed switch port, or a critical misconfiguration. Wrong IP address, wrong subnet mask preventing communication even locally, wrong default gateway preventing access off network, incorrect DNS preventing name resolution, incompatible TCP/IP versions, missing drivers, or that duplex mismatch again. Routing loops can also sometimes cause complete reachability failures.
And intermittent connectivity, the worst kind to troubleshoot.
Tell me about it. Intermittent problems often point towards flaky hardware, a cable with a loose connection that works sometimes, a failing NIC that drops packets sporadically, maybe even a power issue causing device reboots. It could also be a wider network issue like congestion causing periodic packet drops or wireless interference fading in and out.
Broadcast storms again.
Definitely. A severe broadcast storm can make the network completely unusable, leading to timeouts and the appearance of lost connectivity, even though the physical links might still be technically up.
Interference.
Outside interference is a big one, especially for copper cabling. EMI, electromagnetic interference, from things like large motors, fluorescent lights, power cables running parallel to network cables, can corrupt data. Crosstalk from adjacent network cables interfering with each other is also common if cables aren't properly installed or shielded. Using shielded twisted pair, STP cables, can help in environments with high EMI. Fiber optic cable, being light-based, is immune to EMI and crosstalk.
And timeouts. Getting requests timed out when you ping.
Timeouts usually mean the response packet didn't make it back within the expected time window. This could be due to severe network congestion dropping packets, excessive latency, too many hops or long delays, a firewall blocking the return traffic, or the destination host simply being offline or misconfigured.
Okay, a complex web of potential issues. To navigate this, you need good tools, right?
Essential. You need the right tools in your troubleshooting toolkit. Let's run through some fundamental ones. The absolute classic is ping. Yeah, the command line utility. It sends small ICMP, Internet Control Message Protocol, echo request packets to a target IP address or host name. If the target is reachable and configured to respond, it sends back an echo reply. It's the quickest way to verify basic Layer 3 connectivity. Are you alive and can I reach you?
Simple but effective first check. What's next?
Path ping. This is a more advanced Windows tool that combines the functionality of ping and tracer. It sends packets to each router along the path to a destination over a period of time, and then calculates packet loss statistics for each hop individually. This is incredibly useful for pinpointing where on the network path packets are being dropped. Is it the first hop router, the ISP's network, somewhere further down the line?
So it shows packet loss per link.
Yeah.
Very useful. And tracert.
Tracert, or traceroute on Linux Mac OS, is used to determine the specific route, the sequence of router hops that packets take to reach a destination. It works by sending out packets with incrementally increasing time to live TTL values. Each router decrements the TTL. When it hits 0, the router sends back an error message. Tracer uses these replies to map out the path, hop by hop. It helps identify routing loops or unexpected paths.
Okay, ping for reachability, path ping for loss per hop, tracert for the route itself. What about seeing active connections?
For that, you use netstat. This command displays a wealth of information about active TCP connections, which ports your computer is listening on, Ethernet statistics, the IP routing table on your local machine, and more. It's very useful for seeing what connections are currently established, maybe identifying suspicious connections initiated by malware, or checking if a service is correctly listening on its expected port.
Sounds powerful. Any other command line diagnostics?
Windows used to have a great tool called netdiag.exe, often part of the support tools. It performed a whole suite of tests on network client configuration, DNS, WYNS, DHCP, domain controller connectivity, and could even attempt to fix some common problems. While maybe less common now, the idea of comprehensive diagnostic tools is important.
What about DNS specifically?
The go-to tool is nslookup. It lets you directly query DNS servers to look up IP addresses for given host names, forward lookup, or find host names for given IP addresses, reverse lookup. Essential for diagnosing name resolution failures. Why can't I reach www.google.com? Maybe your DNS server isn't working correctly, and nslookup can help verify that.
And NetBIOS, is that still relevant?
Less so in modern networks, but NBTstat is the tool for displaying statistics related to NetBIOS over TCP/IP, like the NetBIOS name table and cache. You might occasionally need it in older or mixed environments.
Okay, those are great for specific checks. What if you need to see everything that's happening on the wire?
Then you need the ultimate network troubleshooting tool, a packet sniffer, also called a network analyzer or protocol analyzer. The most famous open source example is Wireshark.
What does a packet sniffer do?
It intercepts and logs all the network traffic passing through a specific network interface on your computer, or sometimes all traffic on a switch segment if configured correctly. It allows you to see the raw packets, decode the different protocols at each layer, Ethernet, IP, TCP, UDP, HTTP, DNS, etc., and analyze the conversations between devices in excruciating detail.
What would you use it for?
All sorts of things. Analyzing complex application problems, detecting network intrusions or malware activity, monitoring network usage patterns, debugging custom network protocols, learning how protocols actually work. It's an incredibly powerful diagnostic and educational tool. To capture all traffic, not just traffic addressed to your machine, your network card usually needs to be put into promiscuous mode.
Wireshark sounds indispensable for deep dives. Are there any really common quick checks people should always do first?
Absolutely. Before diving into complex tools, always perform the common quick checks. Physical checks. Are cables plugged in securely at both ends? Are the NIC LEDs and switch port LEDs showing link activity? Simple, but solves many issues. Driver status. Check Device Manager in Windows to ensure the network adapter driver is installed correctly and the device isn't disabled or showing errors. Basic configuration. Use ifconfig to verify the IP address, subnet mask, default gateway, and DNS servers are correct for the network segment. Check that the necessary protocols like TCP/IP v4 or v6 are enabled.
Start simple, check the basics. Great advice. Applying all these tools and techniques really speaks to identifying network architecture to facilitate troubleshooting.
It's the practical application of all the theory we've discussed.
One last area before we wrap up, safety procedures and policies. This might seem basic, but it's important in any IT role.
Absolutely critical. This includes knowing emergency procedures specific to your environment. Are there fire suppression systems in the data center? What type are they? Water, gas. Understand fail-open versus fail-close principles. For example, a firewall protecting sensitive credit card data should ideally fail close. If it malfunctions, it should block all traffic by default rather than fail open and potentially let malicious traffic through. Also, know where safety data sheets, SDS, are kept for any chemicals used, like cleaning supplies.
And personal safety.
Basic safety precautions are essential. When lifting heavy equipment like servers or UPS units, use proper lifting techniques, use carts or dollies, and always ask for help. Don't risk a back injury. And crucially, protect sensitive electronic components from static electricity, ESD. Always use an anti-static wrist strap connected to a proper grounding point, or at the very least, touch an unpainted metal part of the computer chassis before handling components like RAM or expansion cards to discharge any static buildup on your body. Following general OSHA regulations for workplace safety is also paramount.
Good reminders. Safety first, even when troubleshooting network gear.
Always, protecting yourself and the equipment is part of being a professional.
Wow, okay. That was definitely a deep dive. We've covered so much ground today. We journeyed right from the fundamental language of data, packets, frames, protocols, the different ways data can flow through the essential hardware like NICs, switches, routers, and cables that actually build our networks.
Yeah, and then we layered on the software, the network models like peer-to-peer versus client-server, the different scopes from LANs to WANs, and all those critical network services like DNS, web, and email that make everything useful.
Then we tackled that crucial OSI model, breaking down communication into those 7 layers, which is such a key framework for understanding and troubleshooting.
And we spent a good amount of time on the strategic side, why network management is so vital, the high cost of downtime, and those 11 best practices to prevent problems proactively.
Right. Moving from prevention into reaction with the CompTIA troubleshooting methodology, the importance of establishing a baseline, and digging into specific network problems and the tools like Ping, Tracert, and Wireshark you need to diagnose them. We really explored everything from why your home Wi-Fi might slow down to how major corporations try to prevent those catastrophic outages.
And if we try to synthesize all of this, connect it back to the bigger picture, especially for students, what really stands out is that success in information systems or related business fields isn't just about knowing how to fix a broken wire or configure a piece of software in isolation.
It's more holistic.
Exactly. It's about understanding the entire ecosystem, from the tiniest bit of data flying across a cable, through the layers of protocols, the hardware infrastructure, the services, right up to the largest global network interconnections. It's about seeing how all the pieces fit together.
And making strategic decisions based on that understanding.
Precisely. Making informed, strategic decisions about design, security, and management that prevent problems and ensure business continuity. This foundational knowledge, covering everything from transmission fundamentals to troubleshooting techniques, is exactly what prepares you for real-world industry challenges and those industry-standard certifications like CompTIA Network plus VNet. It's about building that solid base.
Remember that moment at the beginning when we talked about an entire country losing internet because of one accidental cable cut, or businesses losing millions from a cloud service outage?
Yeah.
Hopefully our conversation today has given you, our listeners, the foundational knowledge and the practical toolkit to be the person who helps prevent those kinds of nightmares. Or, at the very least, the person who knows how to systematically and quickly resolve them when they do happen.
That's the goal, to empower you with that understanding.
So, if you found this deep dive as fascinating and valuable as we did, and I certainly learned a lot, please do us a favor. Hit that like button, subscribe to the deep dive so you don't miss our next exploration, and maybe share it with your fellow students, friends, or future colleagues who could benefit from this.
Yeah, spread the knowledge. And don't forget, all those additional resources, links to documentation, maybe some practice sites we mentioned, they're all linked down in the description below. We've curated those just for you.
Definitely check those out. Before we sign off, here's a final thought to maybe mull over, tying back to everything we discussed. Considering the increasing reliance on cloud services and complex interconnected systems, where do you think the next major network vulnerability or bottleneck will emerge? And how might the principles we discussed today help mitigate it? Something to think about.
Good question. The landscape is always changing.
It is indeed. Okay, that's all the time we have for today. Remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.